G'day, in this video we're going to be looking at how we can apply a magnetic field not just to a charged particle, but a current carrying conductor. This video focuses on dot point 6.2.1. We're moving into inquiry question 2, which asks, under what circumstances is a force produced on a current carrying conductor in a magnetic field? The idea of applying a force to a current carrying conductor, a wire, by a magnetic field is called the motor effect and is the main concept covered in this second inquiry question. The first dot point gets us to look at the interaction between current carrying conductors and a magnetic field. And there's a formula there, F equals Li perpendicular B. There's also a sine theta version. It works quite similarly to formula that we've looked at already in this module. And we'll be looking to apply that formula under a variety of contexts. So our key learning intentions today is to first write an expression for electric current in terms of electron velocity and wire length. That will allow us to come up with the equation down here based on what we already know about forces being applied to charges because of magnetic fields. So what we'll be able to do is take this formula and apply it to our original formula, which relates force, charge, velocity of charged particle, and magnetic field to again derive our core equation that we're learning about today. We'll look at the effect of sine theta on the magnitude of force, and we'll do a little bit of a practice problem at the end as well. So first, let's have a look at current moving through a wire. This is a concept that we have looked at before, but a quick recap will enable us to cover some of the core concepts today. So we know that current is the flow of electrons. Let's say that they're moving to the left in the diagram on this slide. Based on previous definitions, as we've discussed before, all vectors pretty much describe the motion of positively charged particles when influenced by some sort of potential or force. So in the case of I, the current in a wire, it will point in the direction opposite to the flow of electrons. And originally we defined this as I being equal to Q on T. However, we can rewrite this formula based on the velocity of the electrons and the distance that they travel. And that's going to be taking inspiration from our general formula, velocity is equal to distance over time. So what I'm going to do is combine those two formula and write an equation which is no longer based on time, but rather based on velocity of electron and distance they travel. So what I've done here is rewrite my velocity formula in terms of t and substituted in the right hand side into our I equals q on t equation. That gives us I equals q on d over v. By rearranging the equation a little bit to clean it up, we get an equation where we have I being equal to qv on d. Note though that I have changed at the end d to L. A lot of the time when we start talking about wires and current carrying conductors, we usually substitute out D for in place of L. And that, I guess, represents the length of the wire or the distance which electrons are traveling through a wire. So we know that I is equal to QV on L, and we also know that force is equal to QV perpendicular times B, or QVB sine theta. What I'm going to do first before looking at anything else on this side of the slide is combine these two equations to give us our equation for today. So here in this problem, I took my expression IL on Q, which is equal to V, and substituted into our original formula, removing V from that equation. Here, when we do that, we get our 2Q values cancelling out, and we're left with ILB. So either you can write that as IL perpendicular B or ILB sine theta, which is the formula that we have over here. With this formula, what we can do is start to analyze the forces experienced by wires which are placed under magnetic fields. As long as we know the length of the wire in the field, the current flowing through the wire and the strength of the magnetic field itself. This is quite helpful because otherwise we would have to know information about the wire, such as the size of charge flowing through the wire and the velocity of the electrons. These values are much easier to determine and measure. However, we should note that there are some pretty distinct similarities in the structure of both of these formula. In both, we have a force, which is describing the motion of the charged object. There's a force experienced in both formula. We also have B, which is our magnetic field causing the force on the charged object. And here there are some parallels that we can begin to draw between V and I. V representing the velocity of the charged particle, or in the case of a current carrying wire, the velocity or the average velocity of the electrons as they move through the wire. This instead is being represented by I being the current. Now, in any scenario, the velocity of the electrons and the current should, in a sense, be parallel, which allows us to analyze these scenarios in very similar ways. We use our right hand rule just like we did in questions previous in this module. Note that when we are using that right hand rule, our thumb is always reflective of the force experienced by the charged object, that B is our magnetic field and is represented by our middle finger, and our index finger is representative of, I guess, the motion of the charged particle, so to speak, or in this case, the current. Similarly to when we looked at charged particles moving through fields, the angle between the field and the wire in this case is just as important as it was in questions previous. So in instances where the current is parallel to the magnetic field, a force of 0 will be experienced by the wire. If we have perpendicular field to the current, we will experience the maximum force for that particular setup or scenario. And in instances where the current carrying wire is at an angle to the field, the perpendicular component of that current essentially is what contributes to the force that's experienced by the wire. Thus, we substitute in this sine theta component, and that, I guess, will act as the multiplier to decrease the magnitude of force experienced compared to what it would have been if the current and the field were perpendicular to each other. This comes back to sine theta and how it works. Sine 90 is equal to 1. Anything less than sine 90 as we go down to 0 will be less than 1 until we approach 0, where sine 0 is equal to 0. Thus, when you multiply sine 0 with all of the other variables in the formula, you end up with a force of 0 at the end. So our practice question for today, we have a 15 centimeter length of wire carrying half an amp of current at an angle of 35 degrees to a magnetic field. That field has a strength of 30.5 microtesla. First off, we're going to calculate the force of the wire due to the magnetic field, and then calculate the magnetic field which is required to produce the same force on the wire if it was set 45 degrees to the field. Before we go any further, what I want to do first is draw out a little bit of a diagram so that we can begin to talk about the direction of the force experienced by current carrying wire. So in this diagram, I've drawn the magnetic field B into the page. That's our first really important step for this diagram. I've also drawn in the current carrying wire. It's running up and down, and I've defined that the current is moving up. And so the reason that I've picked both of those is it makes it really easy to use your right hand rule, assuming that you were drawing this on paper. So if you were to hold your hand out with the top of your hand facing up and your palm facing down at the page, and you do sort of your right hand rule shape, you should see that your middle finger points downwards, which is reflective of the crosses that I've drawn in my diagram to show that B is going into the page. Your index finger just points forward, which is matching up with the current that's been drawn in this diagram. Therefore, your thumb, which should be pointing to the left if you're doing your right hand rule correctly, is indicative of the direction that the force is going. So because there's nothing in the question which dictates anything about direction, whether it's written or diagrammatic, we get to draw our own diagram. We get to define the direction of all of these forces. And if you want to use your right hand rule in the most straightforward and easy way possible, easiest way to do it is with the setup that I have. You're not trying to bend your hand around in different directions unless there are other additional factors to be accounting for in your specific question. So anyway, that's the assumption that we're going to make, that by the right-hand rule, our force is left in this diagram. That's nice and simple and straightforward to account for. The next thing that I'm going to do is draw up a little bit of a data column, and that should allow us to then find our solution. So when I've done the data column, just note that I've done a unit conversion as I sort of went along for the length of the wire. I've converted that to meters, as well as a magnetic field, which is being converted to Tesla. The thing that we don't know is the force, and based on the variables which we do have, it's pretty obvious to see that our new formula, which is that F is equal to ILB sine theta, is going to be the most appropriate formula to use here. So all we need to do is substitute and solve for F as it is already the subject. So what we should find are two significant figures is that the force experience is equal to 1.3 times 10 to the negative 6 newtons. So that's the first part of our question done. The next part asks about a slightly different scenario. So we're to calculate the magnetic field required to produce the same force on the wire if the wire was instead put at 45 degrees to the field. So what we should do first, again, is put up a little bit of a data column, and that should give us some help in figuring out where to go next for our solution. So it should be pretty obvious that a couple of the parameters are the same in this scenario. We're assuming that the current in the wire and its length is going to be the same. And we can also assume, and it's because it's implied in the question, that the force experienced by the wire is going to be equal to our solution in part A as well. Difference here is that we've got a different angle, therefore the magnetic field is going to have to be a different size to compensate for that change in angle. Now, if we want to experience the same force, but we have increased the angle, that's going to mean that sine 45, which is bigger than sine 35, is going to have a larger multiplying factor when it comes to that final calculation. Therefore, we're going to need a magnetic field, which is slightly smaller to compensate for this increase in angle. In order to calculate for it, we're just going to have to rearrange our core formula to make B the subject and then substitute in. And our final answer there is 2.4 times 10 to the negative 5 Tesla, and that's correct to two significant figures. Thank you very much, everyone. In the next video, we're going to be looking at a little bit of theory that is going to be helpful to us, which will set us up to do a lesson where we complete a couple of practical activities that demonstrate the motor effect. But until then, have a good one.